Now, as the final talk of today, I will give the word to Dr. Eren Uçkan, who is a faculty member of Civil Engineering Department in Alanya Alaaddin Keykubat University, and he is also the head of the organizing committee for the 7th ICES.
Thank you very much, Dr. Erberik and dear participants. And my name is Eren Uçkan. I'm a faculty Alanya Alaaddin Keykubat University, which is a public university in Antalya. I will talk about the infrastructure damages and the challenging issues during the recent earthquakes in southeastern Turkey. Well, infrastructure is a wide subject, and I will mainly talk about the lifelines, especially hydrocarbon, the performance of hydrocarbon and water pipelines, as well as the performance of tanks. So my focus will be on those two subjects. Actually, the earthquake caused significant damage to hydrocarbon water and wastewater systems. There were damage occurred 18 points and natural gas transmission pipelines. And the cause of the damage was mainly, the hazard was mainly permanent ground deformations. Actually, buried structures like long structures are very vulnerable to permanent ground deformations, then vibrations. So this earthquake caused extensive damage to such buried structures because of very high amounts of fault offsets and extensive liquefaction, induced lateral spreadings, and also landslides. So other structures like dams, marine structures, bridges, tunnels, tanks, silos, storage facilities, and pumping stations were also damaged. But in my presentation, I will mainly focus on the hydrocarbon and the tanks. Here you can see we just moved from, we made a field surveys. It was a short one, and we moved from Alanya. Alanya is in southern Turkey, and we crossed the Ceyhan Marine Terminal and then came to Gaziantep and spent a couple of days here to investigate the fault crossing problems of essential lifeline systems. And this is the preliminary fault line, actually. It's before going to the field. And actually, this is then extended. And this is the epicenter of the first earthquake, and this is the epicenter of the second earthquake. So just to give some general information, and this was the most powerful earthquake recorded since 1939, Erzincan earthquake, which was a right lateral strike slip, and it was associated with the North Anatolian fault. And this one was the East Anatolian fault, but with a left lateral strike slip, and the death toll was 50,000 plus. And you will see the loss in buildings over here. So here you can see that the fault was ruptured from here and propagated bilaterally to both directions with 400 kilometers and 200 kilometers in the second one. Here you see the distribution of the contours for a 7 intensity region, which correspond to light to medium damage for buildings in Turkey. Now, after giving this information, what is important for lifelines, especially pipelines, is the ground hazard, peak ground velocity, and also the permanent ground deformations. Peak ground velocity distribution here in the first earthquake, as you can see here, goes up to 175 centimeters per second, and even some cases maybe 200, which is really very high value. Well, this is the intensity measure for the pipeline, as main intensity measure for pipeline, which is subject to wave passage effects, because if you divide this value to the propagation velocity, then you end up with the ground strain, which is the main parameter, damage parameter for buried pipelines. Actually, this was near fault action. All this were needs for action. So we expect body waves. So the propagation velocity will be a little bit higher. but we haven't calculated this ground strain yet. But the velocities are very high, actually may cause damage to pipelines depending on the strain level induced there. But our main concern was the fault and pipe crossings. Here you see the main fault segment, one of the segments of the fault. And before going to the field, we decided which route to follow. And then said that, okay, these are the main, these lines are the natural gas. I'm sorry, yes, this is the natural gas pipeline. And these are main transmission pipelines. And the green lines are the crude oil pipelines. And there's also one more line here, the main transmission line, which is a water pipeline. Actually, mainly the natural gas pipelines damaged because of severe action of fault offsets and also landslides and also for liquefaction. And here in this region, we had the main transmission line for the water pipeline, which was subjected to fault displacement of 5 meters fault displacement, which was about 3 meters in 99 earthquake. So that was a very hard situation for the pipe operators. So I will say that, especially for the pipe operators, this was a big problem. Now you see the hydrocarbon pipelines damaged. These are natural gas pipelines, and these are the fault crossing of the natural gas pipelines. And this one here, as you can see, explosion happened. So this is one unexpected result, as there is crossing angle and orientation angle and the slip direction were in such a way that it caused compression, pure compression in the pipe, causing very high damages or rupture in the natural gas pipeline. So apart from the natural gas pipeline, the transmission line for water transmission line also got damaged. And as you can see, this is the water transmission pipe, which is extended about 8 kilometers from Gölbaşı to Gaziantep and crossing this main line here, somewhere around here. But there was very interesting cases with that, what we observed. First one was that, okay, here, 3 cases. I will show you 3 cases. First one, this is the pipeline just laid inside the tunnel. Here, this concrete tunnel, and designers actually anticipated that there's a fault crossing this tunnel, so that they made this pipeline in such a way that it will be flexible in the axial direction via these rollers. And they converted a continuous welded steel pipeline to a segmented pipe. And here, as you can see, this tunnel is just a tunnel that is this pipe has been laid in. So the lateral deformations, possibly the bending deformations, were accommodated by this tunnel, and the axial displacement demand was actually accommodated by these axial flexible connections and together with these rollers. So this was a very interesting case for the pipeline, a different type of a mitigation measure, and it worked well during the earthquake. So this one was not damaged, but there was an axial displacement demand of 40 centimeters, and then it was extended. So after the earthquake, it was reseated, relocated to its original position now, and it became functional after the earthquake. And the second case was a different, interesting case. It's an especially fault crossing problem. Here you can see this pipeline is a 2.6 meter diameter pipe, which is crossing the main fault here. And the fault ruptured the 5 meters of fault offset. So here you can see this is a left lateral fault and crossing this pipeline and causing nominal compression in the pipe. Because if this were a right lateral, then it would cause a nominal tension, whereas here, because of this orientation, it causes a nominal compression here, causing damage in the pipeline. Whereas this is This was a water pipeline, and it was an elbow with 60 degrees. Just after the earthquake, after the fault rupture, that 60 degrees of crossing angle became 90 degrees. So that was really very high value. And so what is the conclusion? I mean, from now on, the design of pipelines should not rely on standard, on conventional methods, but there's a need for innovative and large or systems which can accommodate very large displacement demands. Here, you can see the natural gas pipeline. Actually, nothing has happened to this pipeline because it was only parallel to the fault rupture. It never crossed it. But here, because of the elbow and because of the crossing angle, this problem really suffered a lot. You can see the situation of the damage in the pipeline after the earthquake. Okay, this is another case, which is a very interesting case, and this is a pub. This is a station and a valve room. Valve room. There's one entering here. This side is entering. There are two pipe sections entering to this valve room. So this is a rigid and buried structure, and as you can see, it doesn't move over here. But this pipeline here, this region was subject to landslide. We expect a landslide action just from looking for the NASA, and we see that this part actually remained fixed, whereas this block moved downwards, causing a pull-out problem for this pipeline. So as the remedial action, this section of the pipe was cut, and the excess of stress was released, and then they made a new section of welding here, and now it's under operation. So this area is a fault crossing area. This area was nearly a landslide area, and this is a very strong liquefaction zone. So you can see how hard situations can these pipelines are being subjected. Well, Turkish recommendations for 2002, we have recommendations both for liquid storage tanks as well as piping systems, and these are based on some basic principles. You have to first adjust the slip direction and the crossing angle, so as to say that the deformation shape is an S shape. But in case of a reverse crossing angle, then you end up with an Z shape, which is not definitely a desired type of a deformation slope. So the main issue of the design is based on forming an S shape. So what is the next step? Next step is to increase this S-shaped length as much as possible. So you play with the backfill material, the burial depth, steel grade, D/T ratio, coating, and internal friction, so as to increase the effective length of this pipe, which will definitely accommodate much larger fault displacement. So the final idea is to increase the effective length. This is a graph taken from Professor Spiros Karamanos, and actually we also finished one PhD work, but I'm not able to share those results. But this is also represents the sensitivity of the fault, allowable fault displacement with respect to the crossing angle. So as you can see, for example, for a crossing angle of nearly 90 degrees or 85 degrees, you will have about 4, if you have a 1 meter of a pipe diameter, you will have about 4 meters of fault offset. So the allowable fault offset for a 5% of tensile strain limit state will be 4 meters of fault offset. Whereas if you have 10 degrees uncertainty in the fault mapping, so when the fault ruptures, if the crossing angle is not 85 degrees, but 95 degrees, then the allowable fault displacement drops down to 25 centimeters. So as you can see, there's a huge definite and there's a huge uncertainty. So that's why the pipe designers should be very careful in defining, selecting the crossing angle, and also the mitigation measures to select it. So in order to be safe zone, usually a crossing angle is less than these regions are being selected. So Oh, okay. For the tanks, we also had problems with tanks, but not very serious tanks problem, even though the peak ground velocities and the ground actions were very high. And this is here, we observed some sloshing damages on broad tanks essentially. Here you can see the height to radius ratio less than maybe 1. So these are crude oil tanks. And here you see other types of tanks and medium cylinder tanks located in Nurdağ region. As you can see, the uplift and the sliding problems, sliding phenomena was observed in these tanks, but possibly because of the sliding and also possibly with limited amount of uplift, there was not much damage observed in the system, in the superstructure, in the tank itself. As you can see, because of the sliding of this tank with respect to its bottom, then it will form some sort of an isolation for the upper structure. So actually, if you don't consider the permanent displacement over here, it worked really well for the tank system itself. So here you can see in the same region, sloshing damage due to sloshing, and these are all closed roof tanks. And the last one was, there's also problem with, this is a fault line crossing tank farm. This is very interesting. So this fault line is passing through the tank farm, causing foundation problems. So this actually a separation of the foundation to the soil over here, and there was not serious damages observed over here, but mainly some piping and connections problems and damage in the pipings and connections were observed. So this is also, we have also seismic design standards for tanks, and we have different performance levels and goals, operational limit state, and damage control, which correspond to design level earthquake and also for BDBE levels of earthquake for the New Zealand Society of Earthquake Engineering. But I think the new trend in here in New Zealand is to shift for the low damage design philosophy because of the downtime cost, and this is what they're performing in New Zealand. Okay, so what are the finally extended pipe damage was observed, and performance-based seismic design charts like the one that I showed you previously is needed for buried pipelines because that will be very helpful for the designers, pipe designers, considering Turkey is a main hydrocarbon hub in the region, and also providing gas and hydrocarbon to Europe. That's an important issue. And innovative methods. Now we understand that with standard design, it is not really possible to tolerate a very excessive fault displacements. So in that case, there are innovative methods are required, especially flexible joints, FRP wraps, geosynthetics, changing the ground hazard. So these are the main issues that should be considered. And for the tanks, mitigating the sloshing response of the tank is an important problem, because by the use of base isolation, you can mitigate the impulsive vibrations or the tank wall vibrations, but it doesn't have a positive effect on the sloshing response. So in that case, there's a question mark. What happens if you don't? So why are you using in isolation, and if you cannot mitigate the sloshing response? Well, using buffers together with the base isolation will make the system much more feasible, much more rational solution. So the most rational solution is to use buffers together with the base isolation. And also we saw that the sliding of the base sliding also worked very well for the tanks itself. And for the, I haven't presented, but there's a need for solutions, simple, economical, and effective solutions for the vibration control of industrial structures, especially silo structures. So especially those bracings. So some BRB, buckle restraint braces, can be very useful. These braces can act like sacrifice themselves during earthquakes and like fuse elements so that they can be replaced just after earthquake. And the last one is the monitoring of industrial and critical equipment, critical infrastructure. So this project was, our field trip was supported by TÜBİTAK 1002C program. And we are also grateful to Gaziantep municipality providing us logistic support and their sharing their information and being helpful to us during our field trips. And we made this with our young colleagues Murat Aksel and Ercan Şerif Kaya and Oğuzhan Ateş from Alanya Alaaddin Keykubat University. And thank you very much for your concern. This concludes my presentation.
Okay, thank you, Dr. Uchkan. So this concludes the talks for today's webinar. I would like to thank all the speakers for their valuable contributions and also to our participants for their interest. I believe dissemination of knowledge and exchange of information will continue in the conference with the participation of many national and international researchers who have worked at the earthquake-affected sites. So I think that this joint conference will be the first and perhaps the most suitable place to make much more fruitful discussions and to share valuable data among the researchers. Okay, so there were some questions, and thanks to our participants, they asked questions and made comments, and I think these were already responded by our speakers. So I don't want to take your more time, but if you have some small questions, perhaps we can answer. Otherwise, I want to just make a brief, give some brief information about the conference and just close this webinar. Thank you, Dr. Okuyucu. Just brief information. So the conference will be in November between 6 and 10. So it will be in Xanadu Resort Convention Center in Antalya. We are expecting, in joint conference, of course, participant of nearly 500 researchers. We have a large exhibition area, and we are expecting more than 50 exhibitors to the conference. There are many different topics, trendy topics in earthquake engineering, in base isolation, in energy dissipation devices. In addition to that, you can also organize spatial sessions. There will be spatial sessions about the Kahramanmaraş earthquake, geotechnical, structural, seismological aspects of the earthquake. And there will be working group meetings, annual board meetings, and all these kind of activities during the conference. And finally, I also want to thank our supporters in this conference, the main supporters, the governmental supporters, and also academic partners who are contributing to our committees, scientific committee, organizing committee, and also non-governmental supporters from all over the world. And also I would like to state that the conference proceedings will be printed in an ebook by the Springer. So Ayşegül Hocam mentioned in the chat, but we have an extended abstract submission deadline up to the 1st of May. And you can see the conference webpage here on the slide. And once again, I want to thank you for your interest and attendance, and I hope to see you in Antalya in November. Thank you very much.